Hello everyone, I Karunanikum, Assistant Professor in Electrical Engineering Department. Today we will discuss about power quality issues in power system. All will find something fruitful in it. We are basically discussing about power quality, monitoring, process and corrective measures and some power quality standard overview. First of all, what is power quality? Any power problem manifested in voltage, current or frequency deviation that results in failure or misoperation of consumer equipment. Good power quality can be defined as a steady supply voltage that stays within the prescribed range, steady AC frequency close to rated value, and as smooth voltage curve waveform. It means it resembles as a sine wave. Power quality mainly deals with voltage and current distortion, frequency deviation, waveform distortion, and the combined effect of all leads to poor power factor. The consequence of poor power qualities are higher energy usage and cost for the industry, higher maintenance cost, equipment instability and failure. The main point to be noted is that power quality at your place of business can have a big effect on your work. You have to make sure the power coming in is of the right quality and that your machines are set to a function properly with power they are supplied. Poor power quality. It is a sufficient deviation in the power supply to cause your equipment failure. Good power quality is power supply is sufficient to the equipment to operate satisfactorily. The waveform is like this when you have your quality of power is good. When your quality of power is not good, then your waveform is appear like this. Poor power quality and good power quality. The difference between is due to poor power quality, unscheduled downtime in your industries, equipment damages, decreased energy efficiency, more flickering and disturbances in output, and more risky environment. Good power quality leads to consistent uptime, increased reliability, increased operational efficiency, predictable and consistent output, safe and efficient workplace. It means if your power quality is good, so your efficiency is also good. Why good power quality is important? Good power quality saves money and energy. Direct saving to consumer come from lower energy cost and reactive power tariffs. Indirect savings are gained by avoiding circumstances such as damage, premature aging of equipment, loss of production, or loss of data and work. There are some recommended practices for power quality. These are the parameters which decide how your power quality. There are 7 main parameters. Number 1, short duration RMS variation. This variation is further divided into 3 parts: instantaneous, momentary and temporary. In instantaneous, sag and swell. Sag means your voltage is dropped and swell means your voltage is increase. Next one, long duration RMS variation. It is divided into further parts: instantaneous and sustained variation, undervoltage, overvoltage, overcurrent. Next one, impulsive and oscillatory types of transient, imbalance in voltage and current, and the waveform distortion. The waveform distortion is due to DC offset, notching, noise, harmonics, interharmonics. 6.1, voltage fluctuations and power frequency variation. Now we discussed all these points one by one. Transient. The voltage and current signal in power system changes its state instantaneously or momentary. The transients are classified as impulsive and oscillatory, whereas impulsive transient are unidirectional and oscillatory transient have swings with change of polarity. Here you see the lightning stroke current that can cause an impulsive transient. Its direction is in only one direction. Here you see oscillatory transient caused by back-to-back capacitor switchings. Causes: arcing between the contacts of the switches, sudden switching of loads, loose connections, and lightning strokes. Consequences: erroneous result in electronic devices, increased temperature, efficiency is reduced, life of equipment is decreased. Here some more example of transient. This is the example of transient in a single phase supply. It look like this, and it is the example of transient in three-phase supply. This transient is caused by capacitor bank energization. This is again another example of transient for low frequency oscillatory transient caused by ferroresonance of unloaded transformer. The subdivision of transient is like this. Transient is in two parts, impulsive and oscillatory. Here impulsive transient. Impulsive transient are shown in nanosecond, microsecond and millisecond. You see that if rise time of the impulsive transient is 5 nanosecond, then the typical duration for sustain that transient is less than 50 nanosecond. If rise time is increased 1 microsecond, then your duration of that transient is from 50 nanosecond to 1 millisecond. If in millisecond, then it is greater than 1 millisecond. It means if rise time is increases, then duration is also increases. Oscillatory transient. Oscillatory are defined for low frequency, medium frequency and high frequency. In low frequency we have less than 5 kilohertz. Medium frequency transient are in between 5 to 500 kilohertz and high frequency transients are 0.5 to 5 megahertz. Here again you see that as the frequency of these transients are increases, then the timings are also increases. Next one, interruption. Interruptions are two types, short interruption and long interruption. Short interruption, if the duration of interruption occurs for less than 1 second, then it is known as short interruption. If duration of interruption occur is equal or more than 1 minute, then it is known as long interruption. So the time is below 1 and above 1. The causes of short interruptions are automatic recloser and opening of the relays, insulation flash over or lightning strokes. Consequences: loss of data and malfunction of data processing of the equipment. There may be a failure and unnecessary tripping of sensitive devices. Causes for long interruption: power system network faults, improper functioning of protective equipment. Consequences: this type of interruption leads to the stoppage of power totally for a time interval until the fault is cleared. This is the example of momentary interruption in which your voltage goes to 0 from this time to this time, and in oscillatory here some small notches are also present, and for some time it gone completely 0. Sag and swell. Voltage swell is defined as the increase in the voltage beyond the nominal or recommended value by 10% to 80% for a period of half cycle. Voltage sag. The voltage sag is defined as the dip in the voltage level by 10 to 90% of the nominal voltage for a short period of half cycle to 1 minute. Causes of voltage swell are large load de-energization, capacitor bank energization, abrupt changes in or interruption of current, change in ground reference on ungrounded phases. The consequences of voltage swells are electronic device and parts are damaged, insulation breakdown, overheating of the equipment. Now, causes of voltage sag: more starting current required by motor, faults in the power system, sudden load demand is increased. Consequences: failure of contactor and switchgear, malfunction of adjustable speed drives. Here, this is the picture for representing voltage sag and voltage swell interruption. So this is the normal voltage. When your voltage is increased from 110 to more than that, then it become a voltage swell. If voltage is decreased below 90%, then it is a voltage sag. Voltage interruption, then it is the complete disconnection of the load. And this is the spike. This is also known as impulse voltage. It is again the example of voltage sag, and this is the example of voltage swell. Now, short duration RMS variation in connection with sag and swell of the voltage, and long duration RMS variation again defined in terms of voltages. Short duration variation is again defined into three types: instantaneous, momentary and temporary, but according to the number of cycle or the time. If your sag is only for 0.5 to 30 cycles, then it comes under the category of instantaneous sag and swell. Momentary interruption comes when 0.5 cycles to 3 seconds. And for momentary sag and swell having duration of 30 cycle to 3 seconds. And for temporary interruption sag and swell having 3 second to 1 minute time duration. So below all the sag swell interruption below 1 minute is under the category of short duration RMS variation. For long duration RMS variation, the terms are changed: interruption for sustain and undervoltage. Undervoltage is represented as sag when it is come in the category of short duration RMS variation. Now in long duration RMS variation it terms as overvoltage, but in short duration it terms as swell. And current overload, when all this parameter is sustained for higher than 1 minute, then all are in the category of long duration RMS variation. Now these are some other example of sag and swell. This is the swell, voltage instantaneous swell caused by single line to ground fault. This is the instantaneous voltage sag caused by single line to ground fault. Here it is sag. And this is the temporary voltage sag caused by motor starting. When the motor start, it takes high inrush current or high starting current, due to which voltage is suddenly dropped, and after motor achieve its rated speed, then voltage again achieve its rated value. Undervoltage and overvoltage. Undervoltage occur when the RMS voltage drops below 90% of the nominal RMS voltage and stay at that level for more than 1 minute. Overvoltage. Overvoltage is an event where the RMS voltage rises above 110% of the nominal RMS voltage and stays at that level for more than 1 minute. Interruption. Here it is the overall diagram which defines how interruptions are maintained. Momentary interruptions are in between 0.5 cycle to 3 second. Temporary interruptions are for 3 second to 1 minute, and sustained type of interruptions having sustained for more than 1 minute. Next one is unbalance and fluctuation. When the voltage magnitude or phase difference between the voltage signal are not equal, then unbalance in the voltage is appear. Causes: large number of single phase loads are present in the system, arising of faults in the system, and the consequences of voltage unbalance is harmonics are produced, system efficiency is reduced, heating or power losses are increased, lifetime of the equipment reduces. Voltage fluctuation. It is the series of random and repeated voltage changes that exist within the recommended voltage. Causes: start and stop of electric ballast, oscillating loads and spikes. Consequences: light flickering and visual unsteadiness. This is the picture which shows the unbalance in the system, and these are the vector. Due to unbalancing, the current is also not equal, and the angles here in the balanced system, all the angles are 120 degree apart, but in unbalanced system all the angles are different, 120, 130 and 110. As in magnitude, here 100 ampere, 100 ampere, 100 ampere if your system is balanced, but here you see the current magnitude is not equal, so this is unbalanced. This unbalanced load create harmonics into your system. Frequency variation. The electric power system is designed to operate at a fundamental frequency. The frequency of system is depend on rotational speed of generator. The variation in frequency are occur when there is an imbalance in the supply, sudden switching of the loads and failure of the generator. The causes of fundamental frequency variations are fundamental frequency variation that should affect the operation of rotating machinery or process that derive their timing from the power frequency. Frequency variation of consequences are much more likely to occur when such equipment is powered by a generator isolated from utility system. Waveform distortion. Waveform distortion is appear when the signal is not maintains or resembles to the sinusoidal nature. Then distortion is appear in the waveform. Waveform distortion has 5 parts, that is DC offset, notching, noise, harmonics and interharmonics. These are the example of the rectifier based loads. When you have rectifier based load in a single phase, the shape of the input current is like this. This is not a sinusoidal in shape. Same is for phase control type devices. Again, your waveform is changes as per the phase control. So again here it is not sinusoidal. Same in both these cases. So as we increase the number of supply or increase the number of pulses in the rectifier, your waveform is more likely distorted. Noise. The presence of undesirable electrical signal or unwanted disturbance in electrical signal. It is generated by interference with communication network, which distort the original signal. Noise. Noise generally distort our original signal and it is present in the communication circuit majorly. DC offset. DC offset is very important because all electronic devices and controllers are using DC supply for their operation. DC offset is defined as the presence of DC voltage in the signal. The presence of this DC offset value shifts the signal by certain value with respect to the reference level. Here the signal is supposed to start from here 0, but due to the presence of this DC offset, it starts from here. This magnitude is known as the DC offset, and this DC offset is added into the main signal and shift this waveform at their level. Notching. It is a periodic disturbances is occurred by the transfer of current from one phase to another in power electronic devices during the commutation process. During commutation process, such type of notch is appear in the signal. Harmonics. Harmonics again is divided into two parts, interharmonics and subharmonics. Harmonics produced due to nonlinear load and unbalanced system. Nonlinear load, this is the nonlinear load which make the current waveform shape is like this, and it is not look like a sinusoidal. And linear load, this is the example of linear load which having the current waveform is looking like a sinusoidal waveform. Unbalanced system. In balanced system, neutral current is always zero. But when your system is unbalanced, so there is different magnitude of current is flow in all the phases, and due to this harmonics are produced and neutral current start flowing because triple N harmonics are produced and added into the neutral. What are nonlinear loads? A load is considered nonlinear if its impedance changes with the applied voltage. The changing impedance means that the current drawn by the nonlinear load will not be sinusoidal even when it is connected to a sinusoidal voltage. Example of nonlinear loads includes diode, SCR and other semiconductor devices. These non-sinusoidal currents contain harmonic currents that interact with the impedance of the power distribution system to create voltage distortion that can affect both distribution system equipment and the load connected to it. Here you see two types of loads are connected, nonlinear load and linear load. Linear load taking sinusoidal current, but nonlinear load taking pulse form current. When these two current mix with the supply current and make the waveform is distorted like this, and when this current is flow into this source impedance, then your voltage supply is also distorted, so it is very dangerous for our system. Here some are common example of nonlinear load. Power conversion technology. Power conversion technologies include inverter, rectifier, cycloconverter, phase controller, SMPS. All these are come into the power conversion technology. Variable speed drives and adjustable speed drive are also example of nonlinear load. All electronic devices like computer, laptop, printer, LED, CFL, all are the example of nonlinear devices. Arcing load and switching operation, they also create harmonics or nonlinear effect into the system. Here VFD is a nonlinear electronic type of devices like computer, fax machine, etc. Fluorescent lamp, ballast, all these are the ballast. Electronic ballast is a nonlinear, and this is the example of linear load. And again all type of new type of bulbs and CFL LEDs are again nonlinear loads. Why nonlinear load a concern today? In past, nonlinear loads were primarily found only in heavy industry applications such as arc furnaces, large variable frequency drives, heavy rectifiers for electrolytic refining, etc. The harmonics they generated were typically localized and often addressed by knowledgeable expert and mitigate by only a passive filters because they are concentrated at the point. But at today's scenario, Harmonics problems are now common in not only industrial application but in commercial building as well. This is due to the new power conversion technologies such as SNPS, which can be found in every power electronic device, and it is highly nonlinear load. Proliferation has made them a substantial portion of the total load in most commercial as well as residential buildings. Harmonics. The harmonic signal are defined as the integral multiple of the fundamental frequency of the system, voltage and current. Generally, harmonics are produced when non-linear loads are connected in the power system. Here you see this is our sinusoidal voltage at 50 Hertz. You see this is the third harmonic example. How we can recognize this? In half cycle we have 1, 2 and 3 cycle. 1, 2 and 3. It means it is third harmonic. If in a half cycle it has 5 portions, then it become fifth harmonics. When this third harmonics is combined with the main signal, then it become like this, and this signal goes to our load. Interharmonics. These are the harmonic observed which are not an integral multiple of fundamental frequency. Harmonics are generally integral multiple, third harmonic, fifth harmonic, sixth harmonic, but interharmonics are 3.5 harmonics, 3.4 harmonics, 3.9 times harmonics. So it is not integral multiple of fundamental frequency. They can appear as discrete frequency or as a wide band spectrum. So these type of harmonics come into the category of interharmonics, in which one common pattern is not followed. Here in positive cycle this pattern is followed, but here this pattern is followed. Again this pattern is followed, because these are the interharmonics, not proper integral multiple of the harmonics. This is the subharmonics. Subharmonics are come under 0 to 50 Hertz. For it is in a frequency which is a non-integer multiple of fundamental frequency, and their frequency is less than the fundamental frequency. When your harmonics come below 50 Hertz, then it is known as subharmonic frequency. This is the harmonic spectrum. It is represented by this. So this is our basic fundamental frequency, 50 Hertz. 50 Hertz. And this is 100 Hertz. This is at 200 Hertz. This is at 300 Hertz. This is at 400 Hertz. If in your system you are having nonlinear loads, then such type of patterns are appear. But if in your system is harmonic free, then all these are absent. Consequences of harmonics. This is the example of when your system is having harmonics, such type of incidences are occur. This is the fire in the transformer, switching tripping and damaged by higher current, and This is the induction motor due to high harmonic current. This look like this, and this is the burning of the capacitor due to harmonics because of over current. So consequences are added losses to the installation and equipment, unwanted overload, heating of motor and generators, unwanted circuit breakers tripping or fuse blowing, unexpected resonance, disturbances in electronic equipments causing logical faults in digital circuits. Now, power quality monitoring. Now, why we require monitor this issue? Because all our equipment measure RMS value at 50 Hz, but the harmonics which are present in our system, they are not at a 50 Hz, and the normal meters are not generally measure that harmonics. So we have to monitor our power quality by different types of devices. So power quality monitoring is the process of gathering, analyzing and interpreting raw measurement data into a useful information. The process of gathering data is usually carried by continuous measurement of voltage and current over an extended period. The monitoring process identifies the following point. Why we require monitoring? So, type and nature of the problem. After the monitoring, we will decide which type of problem is occur in your system. So, next one is characteristics of problem to the sensitive equipment, duration and exact time at which problem occur, coincident problem or known operation that occur at the same time. Power quality monitoring devices. We have number of power quality monitoring devices to monitoring the power: digital fault recorder, smart relays, voltage recorders, power monitoring, special purpose power quality equipments. A digital fault recorder or voltage recorder activates on fault events and records the current and voltage waveform that cause the problem. Power quality meters are capable of calculating a large number of power measurements at extremely high speed. This is the power quality analyzer with the accessory. This is the power quality analyzer. These four are current measuring cords. This is the voltage measuring cord. All these are connectors. Power quality monitoring devices measures minimum, average and maximum values for current and voltage, harmonic spectrum, total harmonic distortion THD, total demand distortion TDD, phase relationship between waveform, power factor and frequency, active power, reactive power, apparent power, active energy, reactive energy and apparent energy. All this measurement all automatically saved in a Excel file when you transfer the data. This is the connection of power quality. This is a 3-phase 3 wires system and RYB, and one is for ground, and this is the type, and this is for single phase power quality analyzer connection. And this is again when your system is having 3-phase 4-wire system and ground and neutral is separate like this, then you connect like this R, Y and B. Here it is black, red and blue, and this is for neutral, and it is for the ground. It is not compulsory to connect like this, but if you want, you can do this. Now, why and where we connect this power quality analyzer? So when we connect our power quality analyzer, first of all we have to find the location where we have to measure all this quantity. So this is the diagram. Here is the utility. From here, this is the transformer. After the transformer, all loads are connected like this. This is one more type of connection in which this industrial customer number 3 is again having one transformer and connected like this. So at this point, for the industry PCC, all utility measures harmonics, and all the industry customer have to reduce their harmonics as at this point. If utility finds you have harmonics and enter into the utility that harmonics, they will penalize you. So it is very important where all the parameters we have to measure. So the point is PCC. PCC is the point. PCC of the power supply network is an electrically nearest to a particular load at which other loads are or may be connected. This load can be either device, equipment or system or distinct customer installation. For this industrial customer, PCC is this. For this customer 2, PCC is this, and for this type of customer, PCCC is this. So it is very important point where we have to measure all the data. So this is again one example. See, this is our general utility, and the voltage waveform is proper sinusoidal, and this is the point of common coupling, because from at this point major loads are connected, and here these motors are connected via diode and controller and converging technologies. Here motor is again having control via SCRs. So these two loads are non-linear, and this motor is not non-linear because it is not having any type of semiconductor device for controlling. So gives sinusoidal current, and these non-linear devices change the shape of the current. Now when these two current meets with the supply current, it make originally current is distorted, and when this distorted supply current is flow through the impedance of the transformer, then the voltage is distorted. Now why we need monitoring power quality? Because to find out the requirement of mitigation of power quality problem, to plan preventative and predictive maintenance, to identify the performance of equipment in power quality disturbances, to analyze and evaluate the sensitivity of equipment to power quality disturbances, to identify and categorize the power quality events and problems. And last one is to identify the source of power losses and distortion in the system. Now these are the power quality parameter, and it is represented as THD, Total harmonic distortion. The ratio of RMS value of harmonic content of the voltage to the value of fundamental voltage. That is voltage THD. If it is current THD, then the ratio of RMS value of the harmonic content of the current to the value of fundamental current. So this is current THD. And the total demand distortion, the ratio of RMS value of harmonic current to the maximum load current. So this is TDD. Now there are some standards we have to follow while measuring and deciding which is the problem is related to power quality. So power quality have some standards of IEEE, IEC and ANSI standard. Power quality standards provide guideline, recommendation and limits to help assure compatibility between end use equipments and the system where it is applied. The standards affect all of the parties, utilities, manufacturer, consumer, etc. These are number of industry standards available that address the correct procedure and methods for performing a power quality analysis. These standards should be reviewed to help better understand the science behind monitoring and correcting power quality. IEC 61000 standard on electromagnetic compatibility. ANSI C84.1 American National Standard for Electric Power System and Equipment Voltage Rating. IEEE 519 Recommended Practice and Requirement for Harmonic Control in Electric Power System. IEEE 1159 Recommended Practice for Monitoring Electric Power Quality. IEEE 1250 Guide for Identifying and Improving Voltage Quality in Power System. IEEE 1169 Trial Use Recommended Practice for Voltage sag and short interruption right through testing for end use electrical equipment rated less than 1 kV. IEEE 1789 Recommended Practice for Modulating Current in High Brightness LEDs for mitigating health risk to the viewers. Now, power quality issues and corrective measure. How we take which type of corrective measures? Power quality issues cannot be resolved completely but can be reduced using the following methods: by power factor correcting circuits, filters active and passive, and FACT devices. Power factor corrector circuits. When the detected reactive power absorbed by the load is more than the compensator rating, the power factor correction obtained by using capacitor bank to generate locally the reactive energy necessary for the transfer of useful electric power. It allows a better and more rational, technical, economical management of the plant. FACT devices used when it is the static power electronic devices installed in AC transmission network to increase power transfer capability, stability and controllability of the network through series and shunt capacity. Compensation. Filters, passive, active and hybrid filters. Filters reduce problem of voltage and current harmonics. there are three type of basically filters: passive, active, and the combination of passive active, that is hybrid filter. Passive filter uses combination of R, L and C. Active filters make power electronic technologies base which cancel the harmonic current component by producing specific current components. Active and passive system combines to form hybrid filter which work very effectively for harmonic and other waveform distortion in the system. Now, power quality problems ultimately impact the end user or consumer. So all utility, consumer and manufacturer have to deal with all these constraints. So they have to deal with engineer, facility designer, monitoring equipment, manufacturer, consultant, power quality equipment, standards and research organization. And in upcoming time, power quality is become a very crucial issue because all the electric vehicles are coming into the market that are non-linear in nature, and they produce huge harmonics, and they distort our supply. Again, microgrids are also using non-linear conversion. By converging technologies, they are also creating a harmonics. So it is a very burning topic. And I finish my presentation here, and last but not the least, at the last, I thankful to Mr. A.S. Tare for providing me some material and guidance for this presentation. He is the proprietor of Udit Electrical and manufacturer of thyristor switched APFC panel, power and motor control centers, harmonic filter. So thank you. If you have any query, kindly write or mail me. This is my mail ID.